So, a quick recap. We were discussing about the effect of a channel length modulation on the MOSFET and with the perspective of designing an amplifier, right? So we have been trying to design a good amplifier that from 30 lectures back. We are still at it. So let's do a quick recap of what we were doing. So this is a NMOS equivalent of a common source amplifier, and this probably was good enough to achieve any gain, provided you had higher access to as high a supply of VDD as you can. However, the problem that we saw was this transistor is not a voltage control current source in the incremental domain, not an ideal voltage control current source. So an ideal voltage control current source incrementally, or an ideal transistor should have been like this, right? So this is GM times VGS in the incremental domain. However, the issue became, due to the presence of channel length modulation, we ended up having a RDS or a GDS, right? So which essentially meant that even if nothing was connected to the drain, right? Here, for example, RL is connected to the drain. Even if nothing were connected to the drain, the gain would have been GM over GDS, right? So in the ideal model where GDS was 0 or RDS would have been infinity, if nothing were connected to the drain, that is, had it been an open circuited load, the gain would have been what? Let's say GDS is 0, which means it's open circuited, and RL is a very large value. Open circuited means almost infinity. Let's assume infinity. Then what would have been the gain? Infinity, right? So that's great. That would have been great. However, we see that in a more realistic model of a transistor, the gain is not infinity, even if RL is infinity. The gain is limited by its own intrinsic behavior, and it's limited by its own intrinsic gain. And as it turns out, in modern technologies, this intrinsic gain can be quite low, in the sense that it can be as low as 10, 5, something like that, depending upon what technology node you are targeting. So if you have to design an amplifier which has a pretty high gain, I mean gains of 100, 1,000, million, something like that, then obviously this is not going to help, right? So simply connecting a very large load or a very large load at the output with the hope that GM times that load will be the gain is not going to happen, because ultimately that load will come in parallel with the intrinsic resistance of the transistor, right? So, and the intrinsic gain will dominate. So then we found out ways of improving this architecture, and the stuff that we saw was, I mean, if again, when I'm drawing it like this, I'm implying that this is an incremental model, because this resistor doesn't exist in its physical form. So what we saw was this current, if we assume this symbol to be an ideal VCCS, this becomes GM times VI or VGS. So the issue was, on deeper inspection, we saw that the issue was this current was getting divided between its own incremental RDS and the RL. And if we have to realize a better transistor, in other words, if we have to realize a transistor which can give us better gain, then we would like to divert all this incremental current into the load, and not its internal resistance. So for that, we had to put something here in between the transistor and the load, which can attract all the current, which can suck in all the GM times VGS current into itself and not divert it into the RDS. And for that, we used one of the current source, CCCS configurations, which was also a common gate configuration, right? So this is where we were. Again, in the incremental sense, this doesn't matter. right? So why putting this transistor M2 would have helped? It would have helped because we know from our previous experience, the input impedance of this is much lower than RL, right? So, and if we do a brute force analysis, we found that this Rin was equivalent to 1 over GM2, right, plus RL upon A intrinsic of M2, right? So, and this should make sense, because if RL were 0, right, the intrinsic gain, the input impedance should have been 1 over GM2. You have done it multiple times, but in the presence of RL, it seems like the Rin becomes 1 over GM2 plus an attenuated version of RL. And that's good. We have been able to reduce the effect of RL at that particular node. Okay. So if you choose the intrinsic gain to be decent, right? If you to some extent, intrinsic gain can be in your control. We'll see how later on. If we choose the intrinsic gain to be high enough, then it is possible to bring down the value of RL to a manageable manageable value. For example, if RL were supposed to be 10 kilo ohm and your intrinsic gain is, let's say, 10, by putting this configuration together, you see that Rin can be as low as 1 kilo ohm, right? Or near about 1 kilo ohm, right? So there is a handle. So as a designer, we always look for what handles we have to influence our design. This is one of the handles that would help us. Okay. So, and then we also were trying to bias this circuit, and we have done this biasing in a different context multiple times. So this requires a VGS, and one way to bias is put a battery or put a voltage divider, a resistive divider to generate the exact VGS. But then we know now enough to understand that that type of biasing is probably not very accurate with regards to change of threshold voltage, change of mobility, and so on. So we would like to bias it with a constant current source. So this is one of the ways of biasing. This is M1, M2. Let me call this M0. And obviously M2 also needs to be at a higher, at some voltage, right? Let me call this VB2. Okay. So, and now if you have to couple the input, you can always couple the input like this. Again, you have seen this configuration multiple times. You can choose this value of R, choose this value of capacitance in such a way that the time constant is large enough, and so on and so forth, right? So I'll not focus on this part anymore. I assume that you are comfortable with how to couple the inputs. So what I would like to now concentrate on is to how to accurately mirror this I naught from the left branch to the right branch, right? So inherently I used the term mirror without really defining it. So these type of configurations, for example, this resistor is not required. Let's say something is connected here. These type of configurations are meant to, so let's say this is one is, these two transistors are same W by L, right? All things being equal, can you comment on the currents on the left branch and the right branch? It should be I naught, right? So it should be identical because VGSs are same, right? If VGSs are same, if both transistors are in saturation, then both currents should be same, right? So this type of configurations are called current mirrors, right? So these are called current mirrors. It's mirroring whatever is happening in one branch into another with regards to currents. Okay, so if we have now, good thing about this is that if we want to, let's say I want twice I naught in the right branch, and I still want to use a single current source I naught on the left branch, what should I do? Pardon? Which one? Right one. And let's say I want double the current on the right-hand side. Yeah, so I can simply scale it by 2. The VGS remains the same, right? The VGS remains the same. So W by L scales by a factor of 2. If both the transistors still are, or if the right-hand side transistor is still in saturation, so that is not a given that you have to ensure. If it's still in saturation, then it is expected that the current in the right-hand side branch will also scale by a factor of 2. So similarly, if I want to scale it by a factor of n, all I have to do is to multiply the W by L, or rather choose a transistor size whose W by L is n times higher than on the right-hand side. The current is, if again the transistors are in saturation, the current on the right-hand side branch will be n times that of left-hand side branch. Okay, so now this should be simple enough. This should have been simple enough. This configuration would have been enough had there been no effect of channel length modulation. Because till now, not till now, till 2 classes back, we had been saying that the current in saturation is only dependent on VGS, right? It's not dependent on VDS. The drain to source voltage does not have any impact on the transistor current when the transistor is biased in saturation. That's what the entire premise has been. But then we saw that it's not entirely accurate, right? Because sometimes you might be able to neglect, sometimes you might not be able to neglect the effect of channel length modulation, which essentially means that if this voltage goes up and down for whatever reason, then this current will also go up and down, right? So the mirroring effect will not be as accurate as you want. Okay, so let me start off with an example. So forget about whatever is connected. Let me call this V0. Something is connected which is setting the V0. Okay. So both the transistors have the same VGS. No issues. But now let's assume the channel length modulation is a reality. We cannot get away from it. So IDS is times 1 plus lambda VDS, right? So this is M1, this is M2. So now if I neglect the effect of lambda, right? If I neglect the effect of this lambda, then obviously the currents in the both branches are only dependent on VGS. And assuming W by Ls are also same, then the currents in both branches will be identical, right? But now if I do not, let's say we cannot neglect the effect of lambda, or cannot neglect the effect of channel length modulation, then obviously the current is dependent on V0, right? It depends on whatever the VDS is in right or left-hand side branches. And if the VDS is not same, right, then the mirroring is not as accurate. Correct? Yes.
Having GDS now in the having the VDS of the left side is the right side. Having the ion is the ion same for M2 and M2?
That's what we are trying to. Okay, so you are talking about this one, top one. Okay, so his question is, so are you essentially asking whatever current is flowing through M1, the same current is flowing through M2 or not? Okay, so that's a good question. So let me answer that also. So assume this guy to be a box. Okay, so you have some effect here. This guy is also a box. You have some effect here, right? But whatever flows out into this box has to come out, right? And similarly, whatever flows out of this, the bottom box has to come out. You mean the left-hand side current? Need not necessarily be, right? That's what we are trying to that's what we are trying to investigate now. Okay. So the current through M1 and the current through M2, right? These two transistors. Okay. So these two transistors are identical because they are in series essentially, right? They cannot but be identical. But it's not necessary now. The current on the left-hand side branch, that is M0 and M1 are identical. Why? Because it is not necessary that their VDS are also identical. Right? So now the requirement has become, in order to have exact current, you need VGS to be same and also VDS to be same.
So also in the left hand side, M0, current is not I0.
Okay, so why do you say that?
Also, we have a GDS.
Okay, his question is the current, this current through this I0 is it same that is going into M0 or it's not same? Where else will the current go?
M0, but also not a GDS 0.
Correct, correct. We have a GDS 0, right? In the incremental domain, we have a GDS. Yes, agreed. No, that's a good question, right? So let me throw it to the class. I know exactly what is your point of contention, right? And it's glad that you brought it up. But let me throw it to the class. So the question is, if this I0, do you agree that I0 flows into M0? Right? But then you say that this EDS, lambda, and so that, I mean, does the introduction of EDS or lambda or Kelvin modulation change the fact that I0 flows into M0? No, it doesn't, right? Because again, it's in series, right? It has to flow. But then something has to change. What changes? VGS changes, right? Because, so let's consider this. So let me name it identically as a top circuit, otherwise I'll get confused. So in this case, if I now consider what is the VGS that is getting developed, right? So let's say in the absence of, if CLM is neglected, the equation that I had to solve was I0 is equal to half mu n Cox W by L VGS minus threshold voltage whole square. And this would have led to VGS is equal to threshold voltage plus, right? Threshold voltage plus overdrive. But if we do not neglect CLM, right? So what is the new equation? Times 1 plus lambda what? And drain to source or gate to source?
Yes.
Drain to source, but as it turns out, the drain to source and the gate to source are identical for M0, right? So essentially this becomes gate to source also, right? So you see now this becomes a power 3 equation, right? Cubic equation, right? So now cubic equation is a mess, right? I don't want to handle cubic equations. So one way to go about analyzing this is to say that to the first order is neglected the effect of ETS, I mean effect of lambda while calculating the value of ETS, right? But then when should we not neglect, right? Sometimes we are neglecting, sometimes we are not. So that is something that we need to be aware of. Now, this is probably best explained through a graph. For example, let's say I say this is ID, this is VGS. Okay. And in case of in our, if this equation is valid, then we say that this is our IDS with respect to VGS. Okay. So now, if this equation becomes valid, right? So we see that this equation is essentially whatever it was supposed to be plus some lambda times VGS. Right? I can break it up into two parts. One part is where channel modulation didn't exist. plus an additional fudge factor, an additional correction factor, right? So that additional now here comes the effect of lambda, right? Whether the effect of lambda is dominant or non-dominant, right? So let's, I mean, if we take some value, let's say lambda is 0.1, right? Let's say lambda is 0.1, and let's say the VGS, or in this case, VDS can, let's say VGS can vary by 100 or 200 millivolts, right? So you see that the lambda times VGS essentially is changing by how much? 0.1 times 0.1, that is 0.01, right? So essentially, how will this curve change? This curve will slightly shift to the right. Right? So now from this, now the question now becomes, if I have to find out the value of VGS from current, essentially what we are trying to get here is that we are trying to find this point, if this is I naught. Correct? But if this split between the red and the blue lines are not enough on the horizontal axis, then it really doesn't matter if I find out the value of quiescent VGS from the intercept at this point or the intercept at this point. Isn't it? So it's all about how much error you can tolerate. So for example, if you have a exponential curve, e power x, then an error in x can lead to a huge error in the ultimate value. But if I have to calculate the value of x from the output, right, then we are doing log. In log scale, small error of the argument doesn't lead to a big error at the output, right? So essentially, a compressive kind of graph gives you that freedom to make the approximation, but an expanding graph doesn't give you the freedom to make the approximation. Right, if that makes sense in a mathematical form, right? So that's why you will see that while calculating VGS of all these configurations, we tend to neglect the effect of channel modulation, right? But while trying to figure out what I is, we generally don't neglect, right? So this is what also we will follow in this course. So let me write it down also. So neglect CLM while evaluating VGS from IDS, but don't neglect right? So this, even though this seems counterintuitive, it should make sense because it depends on what type of nonlinearity we are dealing with. In one case, it is an expanding graph, right? The error can accumulate. In another case, we can essentially say that, okay, it's not too much of an issue. But in either of these cases, one thing is always true, is that if we ensure, regardless of whatever equation you are dealing with, if we ensure this VDS is same on both the branches, then the current will be I naught in both the branches. So there should not be any doubt about that. There is no approximation there. If VGS and VDS are both same, then the currents have to be both same, right? The value of VGS might change with respect to whatever you initially thought it might be, but as long as you can ensure that VGS, the gate to source voltage and the drain to source voltage are identical, then the currents have to be identical, regardless of whatever order the equation is. Okay, so that's, yes. Okay. Okay, so his question is why the red graph should be on the right. So I probably should have explained why I am sketching it like this. So this is assumed that it is not biased with a constant current source, because if it's biased with a constant current source, then the current shouldn't change. So what we are essentially doing is we are sweeping VGS and finding IDS, right? So now if we sweep VGS and vary IDS, the assumption that we generally keep on taking is the VDS is constant, right? But in this case, that assumption is not valid because the thing that we did in this case, I mean, without inherently or explicitly mentioning, I assume that is something like this, right? So or rather, sorry, I didn't tell you. Let me try to. So inherently, what I assumed was when we are changing this VGS, this VDS somehow is equal to VGS. When we are changing this VGS, the VDS is also increasing. Okay, so that is inherent assumption that I made. But I mean, a circuit can be made like this, but it need not necessarily be true all the time. Okay, so if we assume this to be the case, then if I am increasing VGS, then the VDS is also increasing, and then the current on the right hand side is going to increase, right? So that was an assumption, but it's not necessarily that this is always true. For example, if I had made a circuit like this, right? If I had made a circuit like this, then if I increase VGS, the VDS would have. Can you comment if I increase VGS, assuming the transistor is still in saturation, I am increasing VGS, what would have happened to VDS? It would have reduced, right? So then this curve, so let me use a different color. So this is VGS. So this curve would have shifted slightly to the left, right? So because in the absence of channel modulation, the current to the transistor should have been independent of VDS. So the middle curve would have been the one that it would have followed. But in the presence of channel modulation, as I'm increasing VGS, VDS is reducing. Because VDS is reducing, look at the expression here. In this case, you have VDS, which means that effectively the current would have reduced. Right? So the curve would have shifted slightly to the left. Yes.
For same reasons. When VDS is equal to VGS, then for a little lesser value of VDS will be the cheapest.
Correct.
So the rate of
yeah, I mean, there is no doubt about that. So I can understand. No, which case? We are talking about two different cases, right?
black curves for the case when we ignore the CLM.
But which configuration are we talking about? That becomes so. So let me maybe the confusion is because I had approached with this architecture, right? So in this architecture, I naught remains same. I naught doesn't change, right? So if in this architecture, if I naught doesn't change, then so let's say I have I naught and I have VGS, right? So if I have I naught and I have VGS, or rather, let me sketch it. Yeah, I naught is a independent variable. VGS becomes a dependent variable. So let's say at certain, if I neglect CLM and I found out some value of I naught, and I'm trying to figure out the VGS, maybe that point is here, right? So this is let's say neglecting. But if I don't neglect CLM, right? So this point should move up or move down. It should move down, right? It should move down because this is without neglecting CLM. This is because ultimately we are getting the same current, but the equation is now. So in one case, we had half mu n C ox. And in the other case, we are having right. So that's why in the purple case, for the lower value of VGS, you will get the same value of current. but this is particular to this configuration. Right? If the configuration changes, then the curves can also change, because all those curves that we initially drew are for a certain value of VDS. Right? So VDS was a parameter. Right? So now it matched up two of the scenarios. But I mean, this is so I'm trying to spend some more time on this simply because what you will see is that when we have, for example, this type of configurations, and if you get bogged down into algebra of cubic equations, you will never see the end of it, right? So, but circuit design is not about algebra, right? Circuit design is about, I know there is enough complexity, can I deconstruct the complexity and only focus on the stuff that is necessary, right? So the stuff that is necessary in this case is not an accurate value of VGS. The stuff that is necessary is essentially to understand that I need VDS, the drain to source voltage, and the gate to source voltage to be identical. It can be the exact value of that voltage is not necessary. It's not important, right? As long as the transistor is in saturation, all we have to ensure is that the drain to source voltage is also equal to the drain to source voltage of both M0 and N0. If we can achieve that using circuits, then I don't care what values of VGS we arrive at. Right? That's essentially the message. Okay. Okay, fine. So let's then focus on that part. So I hope we agree with the fact that this configuration, yes. Okay, so the conclusion of this with this particular graph is the only conclusion is you cannot neglect VDS while finding out I0. So I0 is now a function of both VGS and VDS, right? You cannot neglect VDS while finding out I0, but you can neglect the effect of channel length modulation while finding out VGS. So that's the only conclusion. The only thing that I was trying to get at with this explanation is why. Right? So had things, for example, had this curve been like going like, so let's say in another kind of device, an ID VGS characteristics would have looked like this. So the better way to draw this is probably like this. So this is for a particular value of VDS, VDS1. For another value of VDS, let's say VDS2, right? Where VDS2 is less than VDS1, this should have been, if we neglect channel length modulation, this guy would have been exactly on top of it, right? But if we do not neglect channel length modulation, now this will go to the left. Okay, so in another device, let's say if, sorry, I think I made a mistake, right? Yeah. Right? So in another set of device, if the lambda would have been very poor, right? And the nonlinearity would have been such that this keeps on expanding, right? This difference keeps on expanding. Then this approximation that we are talking about wouldn't have been valid, right? So what essentially I'm saying is that under what type of circumstances can you neglect this error? And under what type of circumstances you cannot neglect this error? So in case of an under root plot, for example, you can neglect the error. But in case of a polynomial plot, you cannot neglect the error. So that's essentially the takeaway. So that's essentially this message with regards to circuits, in our circuits using MOSFETs. Okay, fine. So now let's concentrate on this structure for some more time. So now we agree that as long as V naught is same with respect to VGS, right? As long as V naught is equal to VGS, the currents in both M naught and M1 are going to be same. But let's say V naught increased, right? So let's say VGS is equal to 1 volt. V naught is 1 volt. Then I know that this current will also be equal to I naught. Right? Because in both cases, VGS and VDS are equal to 1 volt. They're identical. But let's say V naught now increased for some reason. I don't know what. Something was connected here. Because of that, this increased. So naturally, the current on the right-hand side branch, current through M1 is going to increase or decrease. It's going to increase, go up. Right? So that's good. It's going to increase. But the issue is, if depending upon what type of circuit you are making, it's not necessary that change in I naught or change in the current through M1 is acceptable. In most cases, it is not. So if it is not acceptable, then what should we do? We have to figure out a way of ensuring the VDS of both M0 and M1 remain the same. Okay, even if V0 changes, which essentially means we have to put something here. Right? We have to shield M1 from the swing of V0. If V0 changes, I have to ensure that the VDS of M1 doesn't change. That is step one. Step two, we have to ensure that the VDS of M1 is equal to the VDS of M0. Right? So the first step essentially is to put something there so that even if this voltage changes, this voltage is not going to change. Okay, so let me rephrase. So this is in saturation. What I'm essentially saying is that I have to put something here so that whenever this voltage changes, this voltage doesn't change as much. I mean, you cannot ever go to zero. Some change will happen, but nothing is going to change. It's not going to change as much. So do you know any configuration that does that? Yes, and so essentially the common gate configuration that we did before the break helped us in achieving that, right? So if we have, assuming this guy is also biased in saturation, so amount of swing here, if this is delta V naught, the amount of swing here is approximately delta V naught by the intrinsic gain of M2, right? So again, depending upon what is delta V naught, this might be or might not be acceptable, but we agree that this is a better configuration with respect to reducing the swing at the drain of M1. We agree with that? Yes. Okay. So that's another potential solution, right? Why can't we simply connect the two drains? So let's say something is connected like this. So what happens if I simply connect these two? Yes, their VGS and VDS are identical, true. But will this current I naught be the same as here? No, right? Because when current is this part will go like this, right? So that is one issue. The other issue is if you have essentially we are trying to build one of the good things about current mirror circuit is other than the fact that we are trying to mirror the current, we are also trying to essentially make a decent voltage controlled current source, a decent current source on this side. Right? So a transistor is supposed to be a current source, but in the presence of channel modulation, it's a poor current source. Right? So if I connect it like this, what do you think is the output impedance of the transistor on the right or the configuration? If gate and drain are connected, so effectively it's of the order of 1 over GM. Right? So if it's of the order of 1 over GM, it's depending upon what type of GM you choose, it's definitely not a very good current source. And another way of thinking about it is, if I change the voltage here, its current is going to change because it was influencing the gate. It is going to change by a lot because the gate has a dominant influence. Gate and the source has a dominant influence over the transistor current. which means that if this voltage changes, this current is going to change by a lot. So connecting these two, even though if the illusion that VGS and VDS are same, which they indeed are, but it doesn't solve the purpose. The purpose is I want firstly current to be I want in both the branches, which is not guaranteed. Another problem is if this voltage changes, this current itself will change a lot. Right? Sometimes you might want an inaccurate mirroring, but whatever is getting mirrored should not change. That is another requirement at times, but that is also not getting solved in this. Okay. Okay. But a very good question. Okay, fine. So again, you see that the structure that we arrive at is kind of it keeps on making it keeps on making a comeback, right? We have been seeing this structure in multiple contexts over many weeks now, right? We wanted to first we wanted to see that if we can increase the gain of a common source amplifier, this made an appearance. Now we are trying to see if we can make a better current source, this makes an appearance, right? So this kind of this is a very influential structure in analog circuits, and this structure is often called a cascode configuration. Not to be confused with cascade, cascode with the O in between, right? So, and this transistor on top, this is called a cascode transistor. Okay, so it serves two purposes. One purpose will be very clear. We have been arguing on it for a while now. So the amount of current that exits from M1, this current, okay, let me rephrase that thing that I was about to say. So essentially what this does is in case of a common source amplifier, right? In case of a common source amplifier, the job of the cascode transistor is to shield the swing, it should put a shield between RL and M1 in such a way that all the incremental current from M1 goes into RL, right? And not into its own GDS. In case of current mirror, in case of this type of configuration, its primary job is to ensure that whenever there is however much swing you might have at the drain of M2, the drain of M1 sees a reduced swing, right? So essentially the job of cascode is to, in this context, is to increase the output impedance of the configuration, right? So what I am getting at here is, let's say this is biased with VGS and V0, and this is biased with V0. So we can say that this current IDS is I0 plus color. So this is equal to, so let me call this term I0, where I0 is the current without CLM, okay, plus I0 times lambda VDS. Okay, so, and lambda I0, is that correct? Yeah, this is fine. And if you recall, what was the expression of GDS? Lambda I0. So essentially, this is equal to I0 plus GDS into VDS, right? So in a sense, I can say, and in a sense, what we are essentially saying is that, by the way, I mean, this is supposed to be, if you recall, this is supposed to be minus V overdrive, right? This was an approximation. So this was supposed to be this. But we essentially said that V overdrive is negligible. That's why we are neglecting V overdrive. But essentially, this is supposed to be delta VDS, right? This is supposed to be delta VDS because it is on top of whatever you are supposed to, whatever from whatever quotient you were at, how much change of VDS you incurred, right? So in other words, so let me write it in this way. Okay. So what the connection between these two models is, what I'm trying to do is to convince you that while trying to find out the quotient, you can still resort to incremental parameters, right? Because I don't, again, the whole, you are doing all these things simply because I don't want to handle QB, right? It is much easier to handle incremental parameters because we can get them from the quotient equivalent and keep using them, right? So if we resort to this kind of approximation, what we are essentially saying is, as long as we know whatever the I0 was supposed to be in the absence of CLM, or as long as we know GDS, which is easy to evaluate, the amount of change of current that is going to happen in this transistor, the amount of change of current that is going to happen in this transistor, if delta V0 changes, is essentially this. Right? So this is essentially, so delta I0, so delta IDS will be GDS times delta V0, where delta V0 is change from quotient. Okay, so if you think about it, again, it's a quick recap of whatever I have been blabbering on the last 10 minutes. Is if, let's say, you put in an effort and you found out that for this particular configuration, VGS was 1 volt, VDS was maybe 2 volt, and for this case, IDS is 1 milliamp. Right? You have put in a one-time effort and you have found this out. Now I say that for some reason, VDS has changed to 3 volt. So you can redo the entire thing, or alternatively, what you can say is that I can say this IDS new will be this old IDS plus GDS times how much change of VDS has happened? 1 volt, right? Times 1 volt. Right? So this is essentially what I am trying to convince you, that you can do this without too much of a problem, without too much of an error, and without getting into solving cubic equations. Okay, so let me know if you are not convinced with this. I would like to spend more time if you are not convinced, because this will be the backbone of what we are going to do in next couple of classes. Yes, so essentially, whenever you are evaluating QBS, you are evaluating with respect to a certain bias point, right? So in this case, the bias point would have been this, so we are evaluating around VDS equal to 2. But then the bias point is changed from lower to 3 volt. Yes. So great question. This question is, so I am evaluating VDS for a bias point of 2 volt. Now it has changed to 3 volt. Then how can I still use the old VDS? Right? So if you think about it, we should not be able to use the old quotient point even if you are doing incremental analysis. Because when you are doing incremental analysis, you are assuming that signal is changing, current is also changing, which means that every point of the sinusoid, essentially the quotient itself is changing. Right? But why are we still able to do that? Because we are detecting the higher order tendency. We are saying that there is an error, but the error is not revealed. Right? If we are okay with that, then this is okay with the fact of evaluating the bias, evaluating the small signal parameters at certain bias point and using it even when the signal changes, or even when the voltage changes. In this case, the example that I showed, it is corresponding to okay.
Like when it changes from different but according to that formula, on the top right, VDS minus the override. So the quotient voltage should be override.
I mean, now it should, in this case, it should have been P over Y, right? Yes. If I have to extremely big PT, yes, what you are saying is correct. But the issue is we cannot always get that exact value. So whatever we get requires that calculation to give it, right? And then we say, okay, there is small change, we are okay with that while neglecting that. Right? But you cannot neglect it. It's almost like I want 10 and getting 9 and we have to. Yes.
What are the conditions for the?
Okay. So the conditions, so this question is what are the conditions for allowing this? What are the conditions when we can neglect the modulation?
Yes, like I can use the GDS for 2 volt as 2 volt.
Right. So you can use the GDS to 2 volt or 3 volt. That is absolutely okay. Right? You can use either. Right? But you have to be very clear which one you do. You cannot ping pong between two sometimes, right? So that is why it will be your choice, depending upon which one is easy to evaluate. Evaluate the GDS with regards to a certain point that is the easiest to evaluate, right? And then use it, right? So that's the whole purpose of using small signal approximations, right? So again, so think about this way, right? So the question that she's asking is, it seems like a small job because we are finding out small signal parameter at a certain point, and the point changes, and we are still using the same old small signal parameter, right? But if that were an issue, then we shouldn't have been able to do this till now, right? So let's say this is 2 volt, and this guy goes from 100 millivolts sin omega t. So the VGS here is changing from 2.1 to 1.9. Right? Even though VGS is changing by this much, we are still using the same old value of GM. Right? And why was it being allowed? It was being allowed because for certain these changes, we could neglect the higher order values of Taylor series. We can make, as long as we can, essentially goes back to that old Taylor series neglecting thing. If we can neglect the higher order terms, we are good. We can use whatever approximation we can. If we cannot, then we cannot. Right? Okay.